and it was a PhD in mathematical physics. Of course, we know that he's professore ordinario at Università dell'Aquila. He was also for a long time professor at La Sapienza at Roma. And what we know also, he was invited professor in many universities around the world, especially in France, at the University of Toulon, the University of Marseille, University of Versailles, and also he was at Virginia Tech, and a lot of other things. We know that Professor dell'Isola is also an important member of M&MoCS, Mathematics and Mechanics of Complex Systems, and is a specialist of generalized continuum mechanics, and with application in mechanics of materials and structure. So now, Professor dell'Isola, we are listening for you.
Thank you very much. Before I start, I want to tell you that I'm very happy that friends and colleagues organized this presentation for me. I was very surprised, but very happy. When I met Giulio Maier recently, he comforted me when I complained about my too close 60th birthday. He said me, he's a wise man, count your age by friends, not by years. Today, I can say that I'm lucky to discover how many friends I have. The principle of virtual work, a powerful tool for discovery and for metamaterial design. This is what I will try to discuss with you today. As it is a rather delicate subject, I will try to read, because in this situation, words have to be pondered. Mechanics is the first mathematized theory in history of science. Mechanica Problemata is an apocryphal text attributed to Aristotle. In it, the principle of virtual work is already applied systematically to predict the functioning of machines. Look at the study of equilibrium of a lever based on its geometry. The mathematical formalism on which it is based is the Euclidean geometry. On the left, you can see the frontispiece of Aristotle, pseudo-Aristotle text, and on the right, the frontispiece of Euclid translated into Latin. It is the most ancient example of the unifying capacities of mathematical abstraction in the modeling of physical phenomena. The ideas in Mechanica Problemata via Latin and Arabic translations are later transmitted to Lagrange and Piola. Remark the H in Mécanique Analytique. We believe that the Mécanique Analytique by Lagrange is the next most innovative treatise in the field after Mechanica Problemata. Remark that the word mechanics is a calque of the Greek word mechanika. So the H comes from the key, which is there. The theory that it presents has been considered to be controversial since its appearance in 1788. This controversy continues until our days. All results in Mécanique Analytique are obtained starting from the principle of virtual work. We have a kind of grand unification theory. Mechanica Problemata is clearly a primary source for D'Alembert. Here we have the D'Alembert formulation of the principle of virtual work. The translation from French is mine. a system is in equilibrium when the total work done by all interactions involving the system is zero for each virtual displacement from equilibrium. If the principle of minimum energy holds, then the consequent stationarity condition implies a particular form of the principle of virtual work. Therefore, the postulation based on the principle of virtual work is more general than that based on the energy minimum. Lagrange formulation of the principle of virtual velocities. Some commentaries. Lagrange was a clever man, very clever. He was born in Italy, Turin. His mother language was Italian. However, and in Paris, many people pulled his leg because of his Italian accent. His true name was Lagrangia, and in English you write Lagrangian, the adjective relative to him, because British people want to underline his Italian origin. But he could quickly adapt to France, and he changed this name into the French version. Lagrange statement is very general. If a system consisting of bodies or points, each of which is propelled by any power, be careful, Lagrange uses power as a synonym of force, is in equilibrium, and if a small movement is imparted to this system, by virtue of which each point will travel of an infinitesimally small distance, which will express its virtual velocity, then the sum of the powers multiplied by the distance traveled by the point at which it is applied along the line of applications of this same power will be equal to zero if small distances traveled in the same direction as the power are considered as positive and the distances traveled in the opposite direction as negative. You can explain that vector algebra is very useful to our students. If you don't want to use vectors, you need all these words. Lagrange statement can be reformulated even for founding continuum mechanics by using the abstract language of functional analysis and the theory of distribution. The nominalistic issue, which is here, the word power, as used by Lagrange, means what we call force. Somebody claimed that Lagrange did not understand what he was writing simply because he didn't care to read the definitions and the nomenclature by Lagrange. Although a modern formulation of this principle usually includes the use of concepts from functional analysis, tensor algebra, and calculus, one has to agree on these points. First, Lagrange formulation seems so general that it includes all the versions that have been formulated so far. And second, it uses the minimum possible mathematical concepts, only concepts from Euclidean geometry, that are sufficient to rigorously express the principle in its full generality. On the contrary, Truesdell states in 1968 that the Lagrangian mechanics would have a very limited scope. Read in the green, this is the text from Essays in the History of Mechanics by Truesdell. Granted his more modest scope, estimates of Lagrange's performance must remain a matter of taste. With a Baroque language, he manages also to criticize Hamilton, who had called the Mécanique analytique a scientific poem. However, we believe that the style of Lagrange is so clear and modern that one can read it profitably also today. It can be considered in many parts to be a modern textbook. The French of Lagrange is crystal clear even nowadays. The Baroquism of Truesdell is proven by his house. You can see a picture there with his wife. The painting at the bottom, I will show you in more detail in a few seconds. What Truesdell believes that Lagrangian mechanics was the result of the nefarious influence exerted by D'Alembert on Lagrange. What he writes? Lagrange's best ideas in mechanics derive from his earliest period when he was studying Euler's papers. By the way, Euler was a variational man and had not yet fallen under the personal influence of D'Alembert. Therefore, if one trusts Truesdell, Lagrange were a Pinocchio under the influence of the bad boy D'Alembert. He continues writing, analytical mechanics induces the belief that discrete systems and rigid bodies exhaust the universe of mechanical discourse. Okay, so he claims that the commentary shows that Truesdell had not read the last chapters of Mécanique analytique 1802 and the works by Piola, albeit he cites them systematically, because you find the beginning of continuum mechanics based on the principle of virtual work exactly there. The Baroquism of Truesdell is also proven by this painting. His wife, naked, keeps the cut head of Truesdell. This is a typical biblical citation. The true problem is forces or work. Truesdell claims that mechanics is to be founded on the concept of force. Truesdell claims that balance laws, and in particular boundary conditions, can be induced from experiments. Instead, D'Alembert was persuaded that the most fundamental concept in mechanics has to be played by work. It is very strange. I found this quote about Einstein, but I couldn't find the source. As my friend Pierre Sepechet is criticizing me for my lack of sources, I looked for it everywhere for getting a confirmation. So now I call it a pseudo-Einstein quote. Okay? There is never enough experimental evidence that can prove that I'm right, while a single experiment can prove that I am wrong. Truesdell is a follower of Francis Bacon and Hans Reichenbach, the founder of the Society for Empirical Philosophy, or Berlin Circle. In fact, D'Alembert believes that the principle of virtual work must be postulated a priori, and its logical consequences are the predictions to be experimentally checked. The force is a derived concept used during the logical development of the theory. Of course, this concept is very useful in many applications, but without any direct experimental counterpart. Nobody is measuring forces. You measure only displacements. According to D'Alembert, the fundamental and unifying idea has to be found in the principle of virtual velocities, later renamed principle of virtual work. In Greek, they call it the principle of virtual velocities. For a while, they kept the Greek name, then they transformed it. I have found books in which they doubt about if we are talking or not about the same principle. It is the same principle. What is the opinion of D'Alembert about forces? The forces inherent to bodies in motion, obscure and metaphysical entities, which are only capable to spread shadows on a science that it is clear by itself. This is the bad boy. I must warn that, in order to avoid circumlocutions, I have often made use of the obscure term of force, but I never pretended to attach to this term any other idea except those which result from the principles that I have established either in this preface or in the first part of this treatise. So, force is a defined concept, while work is a primitive one. Who was the true author of Mechanica Problemata? Probably Archidas of Tarentum, another South Italian. many times cited by Archimedes. His other works are unfortunately all lost. He founded mechanics on the principle of virtual work, as done later by Lagrange, Piola, Landau, Feynman, Tubin, Midlin, Rivlin, Sedov, Paul Germain, and many, many others. Archimedes was a mathematician who became a statesman. He uses the first formulation of the principle of virtual work in what is most likely the first mathematized text of applied mechanics. Why we are so much interested in understanding how mechanics was at first formulated? Somebody said that because I'm from South Italy, so I wanted to say that. The true reason we want to get hints about invention methods of novel theories. Archimedes was a scientist who wrote on the method in which he was teaching us how he invented the theory of floating bodies. So this is an ancient way of teaching science. We must tell to our students, younger researchers, how ideas were produced the first time in order to teach them how to do. Moreover, Archimedes was a falsificationist ante litteram. Here I wanted to cite Karl Popper. Insofar as a scientific statement speaks about reality, it must be falsifiable. And insofar as it is not falsifiable, it does not speak about reality. Is it worth to ponder about this epistemological and historical debate still nowadays? Is mechanics, it is the most ancient among mathematized theories, still fertile of theoretical problems, and is it still effective in supplying the needed guidance in technological applications? The answer is yes. In fact, one must refrain from the inductivistic belief that laws of physics can be induced from experimental evidence. Bertrand Russell, an outline of philosophy. The chicken noticed that the farmer came every day to feed it. It predicted that the farmer would continue to bring food every day. Inductivists think that the chicken had extrapolated its observation into a theory and that each feeding time added justification to that theory. Then, one day, the farmer came and wrung the chicken's neck. This inductively justifies the conclusion that the induction cannot justify any conclusion. Very elegant. An example of good epistemological practices in continuum mechanics. Paul Germain. Paul Germain has founded the mechanics of continuous media on the principle of virtual work by using the methods of functional analysis. But he has also contributed to this design of Concorde. As ONERA leader and as an expert in fluid dynamics, he designed the boundary layers under the wings of the airplane. The advancement of mathematical tools serve to support and increase the applicative capacities of the same old and always valid principle. You know, COMSOL, ANSYS, next year will not be anymore important to be taught to our students. The principle of virtual work is there since 2,500 years. We can state that the principle of virtual work remains the most powerful tool to be used to favor scientific creativity and also to push the technological advancements in mechanics. Here, we will illustrate this statement by discussing how it is essential in the modern theory of metamaterials or architectured materials. There was a big debate in the French school in the first part of the 19th century. Is negative Poisson effect physical or not? we say that a material is auxetic if when it is subjected to traction, its length increases together with its thickness. Now, using homogenization methods, you can look at the pictures on the right. You can see the differences in the microscopic microstructure in non-auxetic on the left and auxetic materials on the right. So you understand drawing and thinking that you can do homogenization, that positive, negative Poisson effect is possible. However, before homogenization, the problem about the existence of auxetic materials has been solved by Lamé and Green. By the way, the principle of virtual work is not only French or Italian. Hamilton, Green, Maxwell systematically used it. So we should not divide groups into ethnic groups. Probably we should divide people on different criteria. They simply assumed the existence of isotropic elastic energy. Every positive, definite isotropic elastic energy is existing. This is what they believed before finding the microstructure. And therefore, they believed in the negative Poisson effect. Negative Poisson effect, which is used in application to biomechanics. The Gore-Tex used in blood vessels reconstruction is a specimen is shown there. It exploits negative Poisson effect. I'm happy that Andrei Cherkaev is here. I studied a lot his pentamode metamaterial. He did it with Milton, Graham and Milton. A pentamode material has a three-dimensional microstructure which at macroscopic level is at the same time a solid in large deformation while it behaves as a fluid in linear regime. Look, metamaterials can have very strange properties. The fundamental problem in metamaterials synthesis is this one. It consists in the synthesis of materials having some specific physical properties. We must change the paradigm. I suffer physically. I must call it paradigm, which is Greek. We must change the paradigm in our way of doing science. While up to now one looked for the equations describing a specific already existing material, instead, in metamaterial theory, one chooses the equations mathematically represented the desired behavior, and then looks for the microstructure that, once homogenized, is at macro level governed by the chosen equations. The problem is solved in 3 steps. The choice of the continuum theory describing desired behavior, valid at macro level, via a judicious choice of macroscopic descriptors and a suitable formulation of the principle of virtual work. Second step, one must conjecture in a specific class of microarchitectures having a multi-scale structure of the subclass which is candidate to be governed by the chosen macro model. And finally, last step is the identification of the macro constitutive equations in terms of suitably parameterized micro properties in the selected subclass of microarchitectures by identifying micro virtual work with macro virtual work. I hope that Pierre Seppecher will want to continue also after retirement to work with me on this. I said it in public, okay? The micro-macro identification becomes very difficult if one uses models based on balance of forces and balance of moment of forces. Therefore, the conclusions of the epistemological debate give us a powerful tool for conceiving and producing new real-world materials. The micro-macro identification becomes very difficult even if one uses generalized models a la Ehringen, based on balance laws. In fact, at macro level and micro level, one usually needs different sets of kinematical descriptors and therefore different balance postulates. it is very difficult without the a priori knowledge usually given by variational principles to understand which microbalance laws contribute to a certain macro balance law. So, and here the work of Gabriel Piola plays a role. Only by using the principle of virtual work it is possible to get a standardized homogenization procedure from micromodels to get suitably descriptive macromodels. So you start with the choice of macroscopic descriptors. Then you identify microscopic kinematical descriptors in terms of macroscopic ones. Then next step is identification of macroscopic work functionals in terms of microscopic work functionals, and consequently one gets the derivation of macroscopic equations in terms of microscopic properties. The principle of virtual work allows for the determination of well-posed boundary conditions. Given the internal work functional for nth order continua, what is an nth order continuum? Is a continuum for which the internal work or the internal power is given by this formula. You have integral of L times contravariant tensor TL, which we can call L lambda order multipolar stress, which saturates the same order gradient of virtual velocities or virtual displacement. By the way, there is a general theorem in the theory of distribution. Every distribution is built in this way. And do you accept that power work is a linear, continuous, functional in the set of displacements? So do you accept that work is a linear functional in the set of distributions? If yes, this is the most general expression. Okay, then performing subsequent integration by parts on the domain boundary faces. On boundary edges, arriving on boundary wedges, what you get? Using the principle of virtual work, one gets the class of admissible external interactions possible for a given continuum. And we can easily deduce the class of natural and essential boundary conditions leading to well-posed problems. This is green idea. So what you have? You have dual of virtual displacement, a force. You have forces per unit volume on B, forces per unit area on the boundary of B. You get forces per unit line on the boundary of B, but also you get the dual in work of the normal gradient of virtual displacement up to the order n-1. These are what are called by Paul Germain double forces, triple forces, n-1 forces. And you have them on the boundaries, so on the faces, on the edges, and on the wedges. So, essential boundary conditions are displacements and normal derivatives of displacement. Natural boundary conditions are the dual quantities in work of this. Boundary conditions cannot be induced experimentally. The described synthesis procedure is the needed help for inventing materials which do not exist in nature. It is based on the innovative capacity intrinsic in the D'Alembert and Lagrange approach based on the principle of virtual work. Some metamaterials may have properties which appear to be magic. Here I shortly show the conception and construction of acoustic cloaks metamaterials. The microstructure is made by some suitably placed rigid inclusions around the region which must be sound-free. And you see the numerical simulations which demonstrate the metamaterial capacity of hiding a region to acoustic waves. By the way, the problem of synthesis is not new. The mathematical methods which to be used must be similar to those already used for designing analog circuits. I am old enough to have built analog circuits before digital computers became the most used tool. The fundamental theorem in the synthesis of analog computers is the following one. Let us call elementary circuital element resistances, inductances, capacitances, and transformers. For every quadratic Lagrangian and quadratic Hamilton-Rayleigh dissipation function, it is possible to find a graph, and for every branch of the graph, an elementary linear circuital element, such that the obtained circuit is governed by the corresponding Lagrange equations. Therefore, we must find a minimal set of elementary substructures that allows for, via suitable interconnections, the synthesis of every internal virtual work functional. We will show some results concerning virtual work functionals, which are the first variations of a second gradient deformation energy. The basic pantographic multiscale microarchitectures needed for the synthesis of second gradient continua. A pantographic beam. The constituting beams are flexible and are interconnected with perfect pivots. The relevant length scales are 3. Beam thickness, blue pivot distance, the product of the number of cells times the blue pivot distance. The most basic structure is described here. This is on the left, you have the truss version of a pantographic module. So you can get it also as a truss. How we got this? Finding the synthesis of the energy which you see there. So a pantograph is the linearized pantographic beams are the synthesis of the complete second gradient quadratic energy for a beam. The homogenized displacement, U1 and U2 are the components, represent only the position of the blue material points, which we could call Piola points. The positions of red points have no macroscopic kinematical description and are calculated assuming a local microscopic instantaneous equilibrium condition. Remark, for this structure, there are floppy modes, which are no rigid displacement fields corresponding to zero deformation energy. The paper where we proved this is there. Of course, once we got this microstructure, we wanted to deduce the energy for large deformations. In order to get the macro deformation energy capable to describe large displacements and deformations, a mesolength scale is introduced by using Henke discrete springs equivalent to Euler beams. The class of architectures among which we look for our synthesis is that constituted by several constrained Euler beams as represented by their Henke discretization. Placing pantographic beams at the top of a Warren bridge architecture, a fourth length scale is introduced. The height of the beam triangles. All pivots are always assumed to be perfect. So what you get, a third gradient, first 1D continuum. Microinterpretation of macro boundary conditions. This, Professor Bazant was underlining the necessity of this analysis. At macro level, you have got, via integration by parts, some mathematical boundary conditions to be assigned. In the homogenization procedure, you must identify at macro level the constraints corresponding to the constraints which we have at macro level. So if you have this green pivot, blocked pivot, you have a constraint, displacement constraint at micro level. If you introduce a second one in the next blue point, what you do? You introduce a normal derivative. Normal is allowed, of course, normal with respect to the segment of the beam. So it is tangent to the line of blue pivots. So you impose a constraint on normal derivative and rotation at micro level. I also published a paper in Archive of Rational Mechanics and Analysis where we have proven similar results, which improve those which I've proven, are proven in the paper with Alibert and Seppecher. The reactive double force, which is represented in the second drawing, is not a couple. It expands works on elongations. The deformation energy, which next was synthesized, is this deformation energy. This is the deformation energy of a bidimensional plate whose deformation energy depends on the second gradient of in-plane displacement. So it is a novel plate theory. Remark that this energy is incomplete. Only 2 second-order partial derivatives appear. So the only possible floppy mode is there, and if you want to understand why you get second gradient contributions to the energy, it is enough that you see that in the at the micro level, you have that red beam which is bent. So when you clamp short sides, you get this deformation pattern, which, by the way, is impossible to get with first gradient theories. And this pattern is dominated, especially if pivots are perfect, by second gradient terms. Then we invented bipantographic plates. Bipantographic plates are pantographic sheets in which Euler beams are replaced by pantographic beams. So you understand the strategy. We use basic elements for building more and more complicated microarchitectures. Albeit more second derivatives of parallel displacement appear in the energy, bipantographic sheets are not yet a complete second gradient to the continuum. Somebody said he wanted to make a gift for my birthday producing this complete energy, but I've not seen it yet. Okay, this is a reproach. The microarchitecture of bipantographic planar sheets is obtained by assembling a sub-architecture constituted by horizontal pantographic beams and a sub-architecture constituted by vertical pantographic beams having the same central nodes. Vertical and horizontal pantographic beams are interconnected by perfect pivots also. Zero energy homogeneous and horizontal deformations are possible. Zero energy homogeneous horizontal shear deformations are possible. Zero energy homogeneous combined horizontal and vertical shear deformations are possible. And you can include also elongation. So this is the prototype of a pure second gradient material if pivots are perfect. So you cannot say that second gradient energy is negligible. There is no first gradient. Simply. The class of architectures among which one has to look for in order to get the synthesis is again a mesostructure represented by means of extensional and rotational springs. The study of dynamic problems will be achieved by suitably introducing masses in the nodes and mass densities distributed along the extensional springs. We got new challenging well-posedness mathematical problems, and we had to solve them. Russian mathematics is Russian mathematics. In the second gradient energy for pantographic and bipantographic sheets, not all higher order derivatives appear. Nikolsky anisotropic Sobolev spaces needed to be introduced as energy spaces, and boundary conditions must block floppy modes to get well-posedness result. And I must thank Viktor Eremeyev for having decided to help me, actually did the great part of the job, in improving some theorems in this aspect. The unexpected range of validity of continuum theory. This is based on an observation made by another of one of my PhD students, Mario Spagnolo. The principle of virtual work allows for homogenizing the modeling of complex microarchitectures in order to get macroscopic theories that are predictive of their global behavior. So you expect that only the bottom microarchitecture is governed correctly by continuum models. Instead, also the first one is perfectly predicted by continuum models. Look how many holes you have there. The role of functional analysis in continuum theories. The idea at the basis of Piola homogenization requires the choice of the two classes of macro and micro virtual work functionals defined on the set of micro and macro admissible virtual displacement, choice of test functions, the equivalence class of micro deformations corresponding to each macro deformation, micro-macro identification. The identification of micro and macro work functionals on corresponding micro and macro deformations leads to the identification of macro constitutive equations in terms of the relevant properties of micro models. The virtual work functional are distributions in the sense of Laurent-Schwartz, and virtual displacements are test functions. The most known among the many micro-macro identification procedures led de Saint-Venant to identify the elastic parameters in Euler Elastica in terms of specific geometric properties of the beams section and Young and Poisson moduli. The identification is obtained by identifying micro and macro deformation energy following the ideas of George Green. So even British people can be variational. They manage. Paul Germain, using the unifying formulation of mechanics based on the principle of virtual powers, transforms mechanics into a new branch of functional analysis, thus progressing in the scientific program established by Lagrange. On ne trouvera point de figure dans cet ouvrage. One will not find at all figures in this oeuvre. The methods which I expose in it do not demand neither geometrical constructions nor mechanical reasonings, but only some algebraic operations subjected to a regular and uniform advancement. Those who highly regard analysis will see with pleasure that mechanics become one of its branches, and they will be grateful to me for having extended in this way its domain. These are the words by Lagrange. You replace mechanics with continuum mechanics. Analysis with functional analysis, and you will get the Paul Germain contribution to modern continuum mechanics. Pantographic architectures, and I'm happy that Grégoire, I hope he will be next friend added to my age. Pantographic architectures become true because 3D printing. Look at the three-point bending test of a standard beam. Saint-Venant anticlastic deformation of transverse sections. Now, with François Hild, we made some measurements based on obtained using true pantographic objects. This object is made with perfect pivots. Three-dimensional X-ray tomography allows you to look what is happening everywhere in your specimen. So you can explore it inside. You can see where it is denser, where it is more deformed. By the way, observe that no Semvenan anticlastic deformation of the transverse section occur in this specimen. And darker areas are more dense, lighter volumes are less dense, and you can go inside, see where one pivot, this pivot is touching there, the other pivot is not touching there. So you can get a total description and understanding. You can measure deformation, bien sûr, only deformation. The deformation on the upper face is not transmitted to the bottom face, which remains nearly plane. And at the length scale of the microstructure, it is possible to observe some static arching effects. These effects generate a second gradient effect to the macroscopic length scale. We go inside, but I prepared this movie because I wanted to show you that also Cauchy has a role in modern mechanics. He invented Cauchy cuts, an imaginary way for dividing one body in two parts, and he wanted to describe the interaction of one part of the body on the other one. Okay? Now, with the technology available at Paris-Saclay, where François Hilde is, École Normale Supérieure de Paris-Saclay, where François Hilde is directeur de recherche, you can see not only the inside. Look, you can cut this specimen, and also Cauchy imagination becomes true. We studied pantographic beams alone. This was done with another of my PhD students, Emilio Berchesi, and with Simon Oyster, who works with us, is from Stuttgart. I hope I don't forget anybody. This numerical simulation was made because of the skills of Emilio Turco. This material is very strange. It starts behaving like a beam, as a beam, and then it becomes a chord. You have a deformation-driven phase transition. In the first stage of the deformation process, it is like an Euler beam, a little bit strange. Starting from a certain deformation level, it starts behaving as a string. The elongation deformation becomes dominant on the bending deformation. Here, you see the 3D printed materials which we printed with Tomasz Lekshitsky from Warsaw. Here, measurements which we made about the deformation bias test of bipantographic materials. And look, having done the analysis which allowed us to identify the correct micro constraints to get the correct macro boundary conditions, we printed a specimen in which the two last pivots were interacting in order to have the normal derivative equal to 0. So we imposed the new essential boundary conditions for getting these simulations. By the way, I forgot that the shear test of the pantographic beam was done with the group of Wolfgang Müller in Berlin. I hope he will not be upset, I nearly forgot it. So what we get? Physical realization of normal derivative constraints in bipantographic structures. Then we started a collaboration with a group of Zacharias Vangelados and Maria Farsari, plus Professor Grigopoulos in Berkeley. And using multiphoton lithography, we wanted to explore the possibility of constructing pantographic microfabrics. And we wanted to deduce the macro properties starting from the properties of the microcell. And here we started with millimetric architectures. On the right side, you see the experimental setup for, we printed everything for doing an extension test using a compression machine at micro level. But with Anil Misra, we made the measurements which prove how critical the dimensions of the pivots are in the global behavior of this metamaterial. This means that when you change less than 1% of the volume of this microarchitecture, the force which it can apply may double. So you have the proof that the first gradient homogenization hypotheses are not at all valid if you want to understand the behavior of these microarchitectures. And I'm very proud to tell you that both in Paris and in Fraunhofer Institute, where too many people are working on this project, but I want to remind only the name of Maximilian Stiltz, who is the youngest among them, a PhD student, active as only Germans can be. They managed to print perfect pivots using 3D printing. So these are the drawings and the specimens in both metallic and plastic. I did not resist. I'm going close to end. I've shot these pictures myself. These are the pictures. This to prove to Emilio Turco that I can shoot good pictures. These are pictures of perfect pivots, so pantographic structures with perfect pivots. And to the last few slides are giving further evidence against inductivism. Without assuming a priori a theory, it is impossible to design meaningful experiments and to reasonably interpret their result. The classical example is the experiment by Michelson and Moreley. They designed it using ether theory, which was falsified. Okay? In large deformations, it is very difficult to recognize where a material sub-body individuated in the reference configuration is placed in the present configuration. I had a long debate with Francois Hild about this point, because I wanted large deformation measures. Okay? And as in France, mathematicians know experiments and experimenters know theory, he invented a technique using second gradient macro theory first row or first gradient micro theory second row. We predict where each sub-body should be placed and look for this sub-body in the image obtained experimentally, having also taken into account its predicted change of shape. The theory suggests where to find what we are looking for, but the experiment is totally independent in the sense that the theory can be falsified, because if we don't find things where they should be, the theory is falsified. And this was, I think, a very nice piece of theoretical experimental work. Different finite elements and meshes are used to drive the digital image correlation with different models. An example of multiphysics metamaterial piezoelectromechanical microarchitecture will really conclude. The basic concept consists in the transformation of mechanical energy into electric energy and vice versa. A structural element is connected via a distributed array of piezoelectric transducers to a suitably optimized electric circuit. I got a patent with some co-workers in the United States about this, and what you get? Piezoelectromechanical extensional beads in extension, you have seen them down, piezoelectrically damped bending beams, which is what you are seeing now. The colors are the electric charges, and blue and red are the displacements. When the interconnecting circuit is the analog of the structural element, one gets electromechanical beats. The analog of an Euler beam, Timoshenko beam, is there, and when you do decoupling with a plate, the plots of isoelectric voltage lines are on the left. This is the beating of the first mode, the beating of the second mode, the beating of resulting from a hammer strike, which is exciting 12 vibration modes. Then you introduce a unique dissipative circuit, and simultaneously you damp the first mode, the second mode, and the hammer strike. So you should not think that metamaterials are only mechanical metamaterials. We must invent multiphysics metamaterials. The principle of virtual work, as Maxwell has shown us. By the way, Maxwell equations were deduced by Maxwell using a variational principle. So, if I manage to conclude, which model should we use? First gradient, second gradient, micromorphic continua. What else? For a specific specimen, this one, it depends on the scale. Lower than 10 micrometers, quantum mechanics. 10 micrometers, Cauchy first gradient continua inhomogeneous. 100 micrometer, Cauchy homogeneous continua. 1 millimeter, beam theory. 5 millimeters, second gradient continua. Now I've really ended. Thank you for your attention.
And special congratulations for his 60th anniversary lecture. Bravo, Francesco. We have maybe time for a couple of questions. If there are some questions, Patrick. Yes, sorry, Professor Dazzi.
It was a great lecture. Francesco dell'Isola. I have one point which has to do with discussions in the 1990s of the gradient hardening plasticity. At that time, gradient theory was proposed by Hutchinson, Nix, and others, and it was found not to perform well, and in Northwestern we showed that it gives scaling, which is very strange. Exponent, power of size, exponents 3/2 minus. Eventually it was resolved. Professor Huang actually introduced that by his mechanism-based theory, which uses second gradient theory, but only in terms of invariant entering the parameters of the number plasticity. And that was verified by modeling various phenomena, twisting of nanowires, bending of nanosheets, that sort of things. So I think that the one thing, I don't want to criticize your presentation, but scaling, I think, needs to be checked of these theories. if there is such strange scaling theory around that was published in GMPS in my paper, I think that should be considered.
Look, I think that you are raising a very important issue, but as I am too old, I asked to Luca Placidi to start working because he's younger and he has more time. I think that we are working towards studying plasticity damage using higher gradient continua, even if I agree with you, there is not yet a perfectly coherent scheme. I don't know if you are aware that the French school, Marigot and Francfort, started using variational methods in this context, but I think that they were too shy. They did not want to introduce extra kinematical descriptors, at least not enough extra kinematical descriptors. So they are still fighting, although they got wonderful results. So I think that the problems you are raising are important, and we need young people for doing, hopefully, we must trust they will do the best job possible. But if you want, we can discuss about these exponentials, which are a nightmare for me also.
Yes, at the end of the... Do you have a microphone? Maybe. Please.
Masterful presentation, Francesco. Work is only one part of energy, as realized by Kelvin doing thermoelectricity. The same kinds of principles would hold if we include heat. So I'm wondering if there's an extension to a principle of virtual energy rather than virtual work, which would give us equilibrium equations and so forth.
This is another thing too for young people. This is a serious problem, and I don't want to be not serious telling you everything has been done and it is easy. Okay. Ivan Giorgio did a very nice paper in this direction, which we published in the M&MoCS journal, and I think that also we must work in this direction. So I agree with you, but I want to tell you that Gabriel Piola was fighting against Poisson, because Poisson, like later Coleman and Knoll, wanted to study mechanics using thermodynamics. And Piola said, it is useless, not elegant. So when we will introduce heat, then we will face the problem of heat. I have a hint of how making variational heat equations, for instance. Do you know Cattaneo correction?
Yes.
By a miracle, it makes variational the energy. So probably heat equation is not variational simply because they wanted to neglect the speed of the signal finite of the speed of energy. So and this in this paper by Ivan Giorgio, this was. Thanks for your question. It allowed me to cite Ivan. Okay.
Thank you very much. I think that we can close this morning session, and now it is time for the lab. Thank you for everybody.